What will be useful for us once again is this table of symmetries. So we have what we call U1R and U1R. We have psi tilde, lambda. So n 0, 1, 0. U1 R was -1, and here please help me, what is it? Minus NF, how is NC by NF? NC by NF. What's again? R prime. This is the naive R symmetry and this is the real one. Yeah. This is 0, n, 0, 1, minus 1, minus, this was minus n by nf, right? Minus n c by nf. And then we had lambda, which is 0, 0, 0, 0, and 1 and 1. Okay, excellent. So you remember that in the last class we discussed that in the case nf is equal to nc, we discussed that we expected this determinant of M, this Meson matrix, minus MM tilde, minus BB tilde, to be equal to lambda to the power 2nc, which is same as lambda to the power 2nf. We discussed this deformation of the moduli space of vacuum. Okay. Now, at the end of the last class, we outlined a check for this idea. Okay, we outlined a check for this idea, and the check that we outlined was that we were going to try to do this 't Hooft anomaly matching, so that the anomalies from the UV and the IR should match. Remember, now we were talking about global anomalies, unlike global gauge anomalies as we've done in previous lectures. Okay? And we outlined, we could work at different points in moduli space, on this moduli space of vacua. There is no point in the moduli space of vacua that preserves all of the global symmetries of the problem, right? Because either B and B tilde, or M has to be non-zero so that this equation can be satisfied. But if B is non-zero, then U1 left is non-zero. You've got a field charged under U1 left. Similarly, if B tilde is non-zero, okay, you've got a field charged under U1 right. Okay, more seriously, remember the conserved currents here, the final conserved currents were, we looked at U1B, which was equal to U1 minus U1, right? So, no, U1 plus U1, which one was it? U1B. Yeah, so was U1 left plus U1 right. Okay, and we also looked at U1 axial, which was equal to U1 left minus U1 right. Okay, so the charges under baryon number were the charges under U1 plus U1, and the charges on the axial current were U1 minus U1. The axial was anomalous. Did I get the signs wrong? Yeah, you're right. You're right. The one that was non-anomalous was the one under which psi bar psi carried charge 0. And this carry, yes, you're right, sorry. Thank you. Yes. So, exactly. So the axial is anomalous, and it was some linear combination of axial and U1R that gave us the true U1R charge. Okay? So in this table, we shouldn't really be looking at this U1R. We shouldn't really be looking at U1 left and U1 right independently. We should be looking at U1 baryon and this U tilde R1. These were the conserved currents microscopically in the field theory. But you see that B and B tilde each carry charge under U1 baryon. For instance, they also carry charge under U1 tilde R. On the other hand, M, okay, on the other hand, M, if you take a turn on some value of M, that violates at least some subgroup of SUNF times SUNF. Also, it violates, it violates some subgroup of SUNF times SUNF. It does not violate. It does not violate the U1 baryon, because U1 baryon is U1 left minus U1 right, and M is Q times Q tilde, which carries U1 baryon 0. Okay, so it does not violate U1 baryon, but it violates, in general, some subgroup of SUNF times SUNF, and also some group, also some part of the R symmetry, and the R symmetry in general. So there's no vacuum that obeys this equation that preserves all of the UV symmetries of the theory. This is clear, right? So what we're going to do is to look at a vacuum that preserves as much as possible and work around that vacuum to check that the anomalies actually match between UV and IR. This is the game. So let's start with one of them. Let's start with M is equal to lambda times identity. B is equal to B tilde is equal to 0. Okay? It's clear that this obeys the equation, because determinant of M is lambda to the power 2nf, which is same as lambda to the power 2nc in this case, whereas B tilde are 0, so this equation is obeyed. Okay? Now, we want to first see in such a configuration, okay, in such a configuration, what subgroup of the symmetries are preserved. Okay? So let's see how the M, B and B tilde transform under all the symmetries. Okay? So let's add to this here. You're right, lambda square. Thank you. Let's add to this table M, B and B tilde. So let's look at M. Okay, this transforms as N. M is a bilinear of Q with Q tildes. Okay, it's got a bilinear index, so it transforms in bifundamental of SUNF times SUNF. Right? So it transforms as N under SUNF. N, I don't need to say in this case whether it's NF or NC because they're the same. Okay, N under SU, N, right? And, okay, it would have charge 1 under each of these, and therefore charge 0 under U1 baryon and charge, maybe charge 2 under this U1 axial. Not that we care about U1 axial. Okay, then there was, under this U1R, this M had charge 0. Remember, we're talking about the bosonic part of M. Right, it's not the fermions. Okay, and in addition, this M, this guy here will pick up the charge of each of these, but we have to remember it's the bosonic part. So we will get minus NC by NF. So in this case, it's just minus 1. So minus 1 plus 1 the whole to the power 2, which is equal to 0. Do you understand? The minus 1 was this. The plus 1 was the fact that the bosonic part had R charge 1 higher than the fermionic part. You remember that, right? Because the expansion of the chiral superfield was boson plus theta times fermion. Theta carried R charge 1. So the fermion carries R charge 1 less than that of the boson.
This is for NF equals to NC.
NF equals NC. I'm writing the step.
In that case, R and R prime are same.
In that case, R and R prime are the same. Exactly. So that it had to be, it was 0. Exactly. Perfect. Now we can do the same for B and B tilde. Okay. So B was what? B under this doesn't transform under any of the non-abelian things because of the epsilons. Okay. Under U1 left, well, it was a product of n quarks, so its charge is n. Under U1 right, it's a product of n quarks, so its charge is n. Therefore, once again, sorry, B is 0. Okay. Therefore, under U1 baryon, the charge of B is n. Okay. And under U1 right, U1 R, this was 0 because it's just a product of quarks, and this was also 0, same kind of argument. Okay. And then we can look at B tilde. So that's 0, 0, 0. Wait. What am I doing? Yeah, 0 and, yeah, n. This was correct. 0, n, and 0, 0. This is clear? Okay? I've written the charges of the bosonic fields. If I want the charges of the corresponding fermionic fields, I should subtract minus 1 from them. Is this clear? Okay. So, so now we see how M transforms under SUNF times SUN times SUN. It transforms like a fundamental of each of these two. Okay? And therefore, it preserves that subgroup of SUN times SUN in which you identify the SUN transformation here with the inverse SUN transformation there. Right? Because inverse up to a transpose. Because the transformation of M is by some SUN left, U left matrix times M times U R, but we'll do it with a transpose. So that it acts on that side. Now we want identity to be preserved. So if we identify U R transpose to be U left inverse, if we make that identification, then M is invariant because this M is proportional to identity. Our particular background M is invariant because M is proportional to identity. So this point in moduli space preserves not the full SUN times SUN, but only an SUN subgroup of that, sometimes called the diagonal subgroup. This clear? Okay. Now, U1 baryon, both this guy is uncharged under U1 baryon. These two were charged, but they have vacuum expectation value 0. So U1 baryon is preserved. Okay. So U1 baryon is preserved. And we see that nothing is charged under R symmetry. That was our original observation. So U1 R is also preserved. Okay. So with this vacuum expectation value, what is the preserved subgroup? What is the preserved subgroup? Okay. The preserved subgroup is U1 baryon times U1R times 1 SUN. Okay? This part is not broken by vacuum expectation values. Okay? Since this is the part of the UV symmetry that is not broken by vacuum expectation values, its anomalies can be compared between UV and IR. Okay? If you've got some vacuum that breaks a symmetry, it will not be a symmetry of the IR theory. It's nothing to compare. Okay? So we can only compare the vacuum expectation values, the anomalies of this subgroup. Excellent. So now, what we will do is compute these anomalies. So which ones are non-trivial? Okay. Always when we've got a non-abelian, like an SUN, you either have 2 or 0 of them. Because in the anomaly, the expression, there's a trace of T, 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 T. If you have 1, that trace kills you. Okay? So you always have either 2 or 1 or 0. Okay? So we could try various combinations. Let's try. We can try U1 R with SUN square. Or we can try, usually things involved.
SUN square is the part which will come in the commutator.
It depends. Commutator meaning what?
When we find the number, that number is trace of EA times commutator of TB.
Trace of anti-symmetrized TA, TB, TC.
So 2 of those correspond to one symmetry and 1 corresponds.
You can do anything you want, really. Okay? But I'm choosing 2 of these to be the SUN in this case, and 1 of these to be the TC. We could take, if you have 3 U1s, you could take 3 different U1s. Nothing really stops you. Then del mu, J mu of one of the 2 U1s would be F of first, wedge F of second. No problem. Yes, I'm going to look at all possible combinations that are non-trivial. Right? Okay, so this is one place to look. Now, let's list all the ones that we expect to be non-trivial. So let me do that listing. So there's this. Then there is U1B squared, U1R, and U1R squared. Typically, these anomaly polynomials with 1 factor of U1B will just be 0. Okay? You notice that when I took the U1B, it was squared or not there. Okay? The reason is that if we look at one of these anomaly 3-point function, anomaly, whatever you call them, these anomaly coefficients, with 1 U1B, you will get typically 0. I'll show you in one example, because the part from the contribution from one thing and another will cancel. I'll show you that as an example. These are the ones in which both sides will turn out to be non-zero and non-trivial. Let's compute these, and then right at the end I'll compute one with 1 U1B. So you might have thought, what? U1RQ, thank you. U1RQ. You might have thought we could also have looked at U1B times SUN squared, or U1B times U1R squared. And you could, but those are going to be trivial. So let's first compute these non-trivial guys. What? U1, that will be 0 because of trace. SUNs have to appear in pairs. Okay? Now, so let's compute these anomalies. Let's compute these anomalies both in the UV and the IR. Okay. So, in the UV, we're supposed to take the contribution of every fermion running in the, every UV fermion running in the loop. Well, in the UV there are 3 fermions to run in the loop. So let's look at them. This guy here was, so we remember we will always use units in which under SUN, okay, the contribution of a fundamental is 1. Some people call it half, doesn't matter. And the contribution of an adjoint is n, 2n. Adjoint is 2n more than the fundamental. Okay, so we will use units in which we will call fundamental 1 and adjoint n. Okay, so now this is very easy. Let's look at this guy. This guy had charge -1 under U1R. Yeah, this U1R was always this tilde guy, the true R symmetry. Right? This guy had charge -1 under U1R, and it came from fundamental. And so this contribution, the contribution from psi is -1. Is it clear? Contribution from psi tilde is the same. Contribution from psi tilde was -1. What about the contribution from lambda? Well, lambda was just uncharged under SUN, so we just get 0. So we get 0. So total is equal to -2. Okay? Excellent. Now let's look at how that works in the IR. So, what are the fields in the IR? So in the IR, we have to look at the tangent space of this manifold around this point. Okay? If we linearize around this point, this will tell us the trace of the linearization of M is 0. You take M and you say M is equal to M plus delta M, because we've got determinant that will contribute trace. Nothing else contributes to linear order. So it tells us the trace of change in M is 0. The deviation in M is traceless. So the tangent space indices include an M that is traceless and a B and a B tilde. Is this clear? Okay. Now, M that is traceless is exactly an adjoint field under SUN times SUN, under the single SUN. Okay? So we've got, our deviations are delta M, delta B, and delta B tilde. Okay? This guy is traceless. Okay, so it transforms under as adjoint of SUN. Okay, it carries 0 charge. Wait, we have to be careful. Right. So, fine. Now we have to look at the contribution of the fermions corresponding to these quantities running in loops. So we should look at the contribution of psi M, psi B, and psi B tilde. Okay? So psi M here carries charge -1 under U1R, because everything carried charge, all the bosons carry charge 0 under U1R. Okay? But the fermions carry -1 therefore. Okay, so it carries -1 under U1R and then gets the contribution of the adjoint from SUN. So we get -2n from here. Okay. Now let's look at B. This guy will not contribute at all. I'm sorry. And here I forgot that each psi has charge -1. But there were n of them. There were n of them, so this is -n, -n, -2n. This guy gets +0, +0, so we get 0. That's how we get -2. U1R charge, but it doesn't transform under SUN square. It's a singlet under SUN square. Okay, so you see how the anomalies are matching between UV and I. Okay, now let's look at U1B squared U1R. Okay, so under U1B, each psi carries charge 1. So U1B squared is 1 and each U1R charge is -1. So we get -1, but then there are n such psis. So -n, and U1B, of course, lambda carries charge 0. So +0. So we get -2n. Right? Now let's look at this guy. Psi m is uncharged under U1B, so it doesn't contribute. So we get 0. Psi b carries charge n under U1B. Okay. Under R charge it's -1. No, but it looks like -n square. Right? Because charge times charge. What am I doing wrong? Looks like if I report it as I see it, I'm saying -n squared, -n squared, -2n squared. What am I doing wrong? Just 1 minute.
What about the left side? U tilde B.
It was square, but it was always 1 square, and then that appeared nf times. You see, it's the difference between. Just let me see. What am I doing wrong? Just a minute. Sorry, just 1 month.
So the U1 tilde R charge for the U fermions till N.
For the which fermions?
For the psi fermions, because U1 tilde is minus N over NF and you multiply by NF, so 1 N is left.
Why do we multiply by?
Because there are NF of them.
Yeah, no, but the way I'm thinking is we do the loop and then we sum. So each of them gives the contribution.
1 plus 1 plus.
Yeah, 1 into minus 1.
And then you multiply by NF.
And then I multiply by NF because there are NF of them. Was that wrong?
I was multiplying first.
Yeah. Yeah. Sorry, just give me 1 minute. Where am I messing up? Yeah, what am I doing? Sorry. What a minute, sorry, give me 1 minute. Oh. Oh. I'm sorry. This was n square. This was n square because psi's carry color indices as well. You see, as far as these global symmetry indices go, every psi field, every fermion contributes equally. Now, how many psi fields were there? There was psi, I, A. A was a color index, I was a flavor index. As far as the global symmetry indices go, you don't care. The total number you will get is n square. In the previous case, we didn't have that. In the previous case, we didn't have that.
This M should also be multiplied by that.
What?
In M also we contract the.
M is contracted. So M has no color indices.
think you wanted to make change in the second.
That's what I meant, sorry. I'm sorry, thank you. You see, the fermions, how many fermions are there carrying U1 baryon charge 1 and U1 R charge minus 1? There are n square of them, right? These fermions are some color and some flavor. Is this clear? Now, you might wonder, have I messed up? Have I messed up? First line. Yeah, let me look at the first line again. Okay, I think this is right. Now let's go back to the first line as you people correctly are telling me to do. Of course, his first line was correct, but I gave you the wrong words. I'm so sorry about this. You see, I got -1 and -1 because these were fundamentals under SUN. Once I use fundamentals under SUN, I'm not allowed to multiply by n because of indices under SUN. We've taken into account the TA structure under SUN.
But that is flavor SUN. Right?
Exactly. Therefore, I should multiply by NF for color. Okay? So, in the first line, I multiplied by NF, I should have multiplied by NC. I did it wrong, but I got the right answer because we were doing NF equals NC. Right? So I should have multiplied the first line by a factor of n. That was actually NC. That's why it became -1, -1, so -2 times NC, which is -2n. And then it matched. On the right-hand side, we never have any color indices because these are all gauge invariant fields. Okay? On the left-hand side, we need to worry about the color indices of the things we multiply. Is this clear? Okay, excellent. Okay, now that we think we've got the rules right, let's see if the third line works. Okay.
N squared is actually a NF times NC.
What?
N squared is actually a NF times NC.
Exactly.
N is actually an NC.
Yes, exactly. This was n squared was NF times NC, and this n was NC. Okay, and here everything, of course, was just NFs because there was never any NC. But we're working in the case NF equals NC. That's why it worked. Okay, exactly, good. Now let us go through this guy. Every field here, every field in the game has U1R -1. Because all scalars had U1R charge equals 0. So all fermions have U1R charge -1, except of course lambda, which has U1R +1. Okay, so these two have -1, and all the composite fields have -1, but lambda has U1R +1. Okay, so now let's work out how this goes, and let's try to keep our wits about us. Okay, so let's do these guys, the size, the contribution from psi. Okay, here we're going to get 3 -1s. So we'll get -1, but how many of them? Well, n square. Right? So we'll get -n square from psi. From psi tilde, we will get -n square. Same argument. Okay. What about from lambda? We will get plus n square -1 from lambda. Okay. And so totally we get -n square -1. Is that good? Okay. Now what about from the composite fields? Okay. So from the composite fields, let's see, every field in the game carried U1R charge -1. So we'll get -1 times the number of such fields. So from psi m, we'll get minus of n square -1. From psi b, we will get -1. And from psi b tilde, we'll get -1. Adds up to minus of n square plus 1. So it works. Is this clear? After correcting all my mess ups, it actually works. Okay. You could ask, suppose you tried to anomaly match those things that were broken, you wouldn't even know what to do. Because the tangent space fields transform in only the preserved symmetries. Let's try one more of this. Let's try one more of this before we declare success. Is this clear? Any questions or comments about this? Okay. Excellent. Fine. Let's now try the point where m is equal to 0, b is equal to b tilde is equal to lambda to the power n. Okay. So m is equal to 0, b is equal to b tilde is equal to lambda to the power n. Okay. Now you see what is preserved here. We have SU n left times SU n right preserved. Okay. Each of these carry baryon charge. So baryon charge is not preserved. Nothing carries R charge. So let's call this left and right to distinguish between. And then there's times U1R. Always this is this U1 tilde, okay? That's the actual U1R symmetry. In this case, there's no difference. NF is equal to NC. Is this clear? Okay? So the preserved symmetry is SUN left times SUN right times U1R. Oh, something I promised you before was in this case to what about those things with one U1 baryon or three U1 baryons? We're going to get 0. Do you see why? Can somebody tell me why?
Sorry, what?
Suppose we tried a triple product, okay, with one U1 baryon. Let's say U1 baryon, U1 and times U1R square. U1 baryon charge is 0, not for all fields. Right? We got some non-trivial thing for U1. Yes. So, but I'm claiming that if we take odd number of U1 baryons, we will get 0. Let's look at the UV first. Why will that be? Exactly. Psi and psi tilde have identical properties under everything else. That was preserved, but had opposite U1 baryon charges. So the contribution of psi and the contribution of psi tilde will just cancel out. Okay. Similarly, in the IR, B and B tilde were identical in every other way, but they had opposite U1 baryon charge. So their contributions will cancel out. So I didn't write those other ones with the odd number of U1 baryons simply because we will get 0 is equal to 0 on both sides. That is never very convincing, right? Okay, I'm writing the non-trivial ones. Is this clear? Okay, excellent. Fine. So we have this m is equal to 0, b is equal to b tilde as lambda to the power n, and that preserves this symmetry. Now we want to look at the composite operators, how they the tangent space, how it transforms under the symmetry. Okay. Now, first we have to linearize. So if we linearize, we will get delta B times plus delta B tilde times lambda to the power 2n is equal to 0. Right? So we can use this to, for instance, solve for delta B tilde in terms of delta B. Okay? So what are our linearized fields? Our linearized fields are delta M, which is now an NF cross NF matrix. The trace is not removed. And delta B tilde has gone. So it's delta B and delta M, which is a full NF times NF matrix. Is this clear? Chintan, you're looking?
Yeah, this side.
This.
So we are expanding around B equals to B tilde.
B is equal to B tilde is equal to this. Okay? And you see, we've got det. The equation we are expanding is det M minus B B tilde is equal to lambda to the power 2nc. Expand around 0, you need at least n elements in M to trigger M. So expansion of determinant of M up to nth order is 0. We work to first order, certainly it's 0. Okay, so this doesn't contribute. Here then I just linearize this. Change product rule. Right? So the linearization is entirely in the BB tilde space, that's the point. Okay? And so we can solve for delta B tilde in terms of delta B. For instance, or delta B in terms of delta B tilde. The fact that baryon number was broken by this vacuum tells us it doesn't matter whether we use delta B or delta B tilde. Because delta B and delta B tilde have identical quantum numbers for everything other than baryon number. But baryon number is not one of the preserved symmetries. So as far as preserved symmetries go, these guys have identical quantum numbers. Okay? So let's choose to use delta B. Okay? And now once again we can go ahead and list what we think would be. So let's.
Delta B and 2n square M. Delta M.
I didn't say that again.
We have delta M also, right?
We have n square fields in delta M.
2n square, right?
Why 2n square?
Okay, real 2n.
Yeah, but a chiral multiplet, as a chiral multiplet, there are n squared chiral multiplets. Right? There's n squared chiral multiplets for delta M and one chiral multiplet for delta B. Clear? Okay? Okay. And under SUN times SUN, how does delta M transform? Clearly like bifundamental. Okay? How does it transform under U1R? Well, it's uncharged, but that means its fermion will transform the charge -1. And what about the delta B? Under SUN times SUN, it's uncharged, and its fermion transforms as -1 under delta R. Okay, so all our charges are very clear. Right? So now let's list the potentially non-trivial guys. We could have SUNF square times U1R. Right? We could have SUNR square times U1R. Let me just check first. I've got this. Yes, so we could have SUNF squared times right. We could have SUNF squared times delta, or you could have SU n r squared times U1 r. And then you could have, basically it's U1 r cube. Okay. Now, under SUNF and SUNR, we're going to get the same. These are basically the same thing. But okay, let's just work them out. Let's do first from the UV. And then there's the IR. Okay. So let's see. Left and right, sorry. And everything here is the actual U1R. Right? So let's compute this from the UV. So let's see. From the UV, psi is a fundamental under SUN left. Okay? So by our rules, this contributes with a 1, because fundamental contributes 1. But there are NC of them. So we will get minus NC from psi, minus N from psi. Minus because every field has U1R charge minus. Clear? Psi tilde does not contribute from SUNF, so that's 0. And lambda also does not have SUNF, so that's 0. Okay, this N here was an NC. Okay. On the other hand, of our fields here, delta B does not transform under SUN n left. Delta M does. It transforms like a fundamental, but there are n such fields because the SUNR fields go along for the right. Right? So you get minus n from psi m and psi whatever, b is 0. So it matches. Notice here this n was an NC. Here this n was an NF. But they are equal because if we are at NC equals NF. All clear? Okay, excellent. Clearly, this one is identical, it's just that psi and psi tilde switch roles. So we get psi 0, psi tilde minus n, lambda 0, and from here we get psi m is minus n, and psi b is 0, so we get minus n. All good? Okay. Finally, for U1R cube, now let's work that out. That is, of course, very easy. U1R cube, there were n square psi fields. Okay, so we get psi is minus n square. There were n square psi tilde fields of minus n square. And there were n square minus 1 lambda fields. So we get plus n square minus 1. So the total is, as before, minus n square minus 1. Minus n square plus 1. This is the same calculation as we did last time because in the UV it's the same. It's U1R cube is just the same. Right? Okay. Now, on the IR side, U1R cube, well, every field has U1R cube minus 1. How many fields are there? N squared from M and 1 from B. So it works. Okay. So for this particular case, I worked out the anomaly matching conditions in great detail for you. Just that so that you see that there's no trickery going on. And there's no matching. It's not a difficult job, right?
You chose these kind of solutions to preserve these symmetries.
To preserve these symmetries. Now, as big as I can. When I try to choose things that will preserve less symmetry, the conditions are less stringent. Yeah. So, I haven't ever checked it in detail, but I think one can convince oneself that there's basically no point in the moduli space where these symmetry matchings will not ensure anomaly matching everywhere. Okay. Right? Okay. Maybe we should have a shorter class this time. Okay. Is this clear? Okay. This is all I wanted to say about NF is equal to NC. Any questions or comments about it? Any questions or comments about anomaly matching? You see, this anomaly matching business is useful beyond this example. Because as you have seen, it is a general tool one can use to try to check the consistency of a proposed low energy description of a UV theory. Okay? And therefore is very powerful. Right? You feel that, okay, I've got this theory, such and such theory, and I think that in the IR it will reduce to such and such effective description. Well, you can check that. Okay? You can oftentimes you can check that using this anomaly matching condition. Now, people in modern times have developed this anomaly matching condition to an art. You know, these are the simplest examples. One can also check matching of anomalies of discrete anomalies. In fact, in three-dimensional field theories, typically there are no continuous anomalies. Odd dimensions, you typically don't have continuous anomalies. But you have discrete anomalies. So these discrete anomalies need to match as you go across UV and IR. Then people also look at anomaly matching for anomalies of, higher form symmetries. Do you know what a higher form symmetry is? Okay. A higher form symmetry is, you see, you have symmetries every time you have conserved operators, and every time you have conserved charges. Okay. A conserved charge is some integral that takes the same value, okay, no matter where that integral is evaluated. Okay. Now, in a normal field theory, local operators carry a charge. Okay. And that charge can be evaluated by some surface that surrounds the local operator. We evaluate, so to speak, integrate J0 around the surface, more precisely J dot n around some surface that surrounds the operator. And the fact that the charge is conserved is the statement that the answer you get for this integral doesn't depend on which surface you choose. As long as you don't pass a charged operator through it. And if you deform your surface without ever passing through charged operators, the answer for this surfaces is the same. Okay. Now you can ask yourself, by the way, one of the nice things about conserved charges is that they can be non-abelian. I have one charge here and another charge on top of it. That's not the same as the second charge here and the other charge on top of it. Okay? So it could be that QA, QB is not same as QB, QA. This is, I'm just telling you the things that we normally say about, perhaps a slightly different language about charges. Now, suppose instead we were looking at objects that were charged under a symmetry that were not points, but instead were lines. Then the thing we would measure to measure the charge is surround this line by some codimension 1 surface on a spatial slice. So we would be surrounding this line by some codimension 2 surface. And then this codimension, the idea is that you would get the same charge no matter whether, I mean, as long as you wiggle your surface around in a way that does not cut this line.
This line is in the space direction or?
It could be in either, but let us imagine to start with that it's in time. Okay? So let us imagine that it's in time, and let's say that your surface is in space. Now you wiggle this around, and you will get the same answer as long as you don't cut one of these lines. It could be like the Wilson, it could be like a Polyakov line, it could be like a Wilson line moving in a time direction, for instance. It could be the, yeah, fine, right. So now you see in this case you also have some sense of a conserved charge because it's some integral whose insertion into the path integral gives you the same answer no matter what surface you evaluate it on, as long as you don't cross some particular other surfaces. Okay? So in some sense this is also a conserved charge. Notice, however, that in this case life is a bit less interesting, because if I've got one charge measured here and another charge measured here, okay, there is no sense of ordering between these two charges. I can make this guy bigger than this guy, or that guy bigger than that guy, without ever going through it by going up and coming back down. Do you understand? I have these two smoke rings. I can take one through the other, make it big, come back around, do whatever I want. Topology doesn't allow you to order these charges. This tells you that these conserved charges are always abelian. Always have abelian structures. Okay. Now this kind of charge is what people I think call a one form. Now instead of a one-dimensional charged object, you can imagine a two-dimensional charged object, and so on. Right? There's no end to this game. Okay. The point of these generalizations is that there are natural contexts in which these symmetries arise. For instance, when studying gauge theories. Okay, and you can take the stubborn point of view that you don't want to consider such symmetries, but you may be forced to. For instance, something that has a line type charged operator, when you do dimensional reduction, you put the theory on a circle, that line can wrap the circle and become a point type charge. So if you can take the point of view that you're only interested in point type charges, but even from that point of view, you'd be foolish not to look at line type charges if you are interested in things like dimensional reduction. Okay, so people have studied these kind of symmetries, studied what it means for these kind of symmetries to be anomalous, and looked at anomaly matching conditions for these kind of symmetries as well. Okay, so the two big generalizations are to discrete symmetries and to these higher form types symmetries. Okay, this adds to your toolkit of what you can do to constrain low energy physics. Discrete symmetry is very useful. The high form symmetry is also sometimes useful.
But you can explain how you want some gauging and all. I don't know how.
You know, the gauging was not really necessary in my opinion. You know, the argument was basically that if I do something, do I preserve a symmetry? Right. Anyway, it's certainly claimed that this anomaly matching should continue to hold for these things. For the discrete symmetries, you can also you can gauge. It's like orbifolding. Right? So suppose we've got a field theory invariant under parity. Now you can orbifold the theory. Treat parity as gauge, like we sometimes do on the well sheet of the string. Okay? That doesn't involve a gauge field, but it's still a gauging. Okay, for the higher form symmetries, I'm unsure about this gauging language, but certainly people claim that the anomalies should continue to match. Possibly there's a gauging language as well. Yeah. Okay, so people have developed this anomaly matching basically to an art now, have really developed it very, very far. And if you're ever interested in making a conjecture about the IR behavior of some field theory, one of the first things you should do is to check that anomalies match. Okay, as you've seen that we did. Yeah. Okay. That's all I wanted to say about NF equals NC. Any questions or comments? Otherwise, let's move on to NF equals NC plus 1.
Before checking this anomaly, how everyone came up with this term on right hand side lambda, was it dimensionally we see that?
Dimensionally we see, but the real way I believe that Seiberg came up with it was the argument we gave in the last class. That is, let me remind you of the structure of the argument. The point is that what you're doing at NF equals NC is not independent of what you do at NF is equal to NC minus 1. You can flow to it. Okay? So, suppose you add a superpotential to your, a mass superpotential, like a bigger mass, and then arbitrary other smaller masses. Okay? That bigger mass takes you to NF is equal to NC minus 1, from where you can use the Affleck-Seiberg superpotential. Okay? Then you can compute all the lower m's, the m's with indices not equal to NF, from the Affleck-Seiberg superpotential. By matching the value of the superpotential, you can also compute m, NF, NF.
But in that case, you match with the superpotential, which is just m and f.
Yes.
There is nothing else.
Nothing else. Right? Let me remind you of the logic of that. This, I believe, is how we actually came up with it. Then the rest is checking. But, so, I don't know, okay? This was before I, right. But let me give you a conjecture for how we worked. Okay? The conjecture is this. Classically, we have det m is equal to b tilde. And if b and b tilde are 0, det m is equal to 0. Okay? Seiberg must have tried to see whether that was true quantum mechanically. Immediately, it's two-line argument that there's no superpotential. So there's a moduli space. Is the equation for this moduli space the classical one? Okay? Then he did what we talked about last time. You turn on, let me call it x, okay? X, NF, NF. I think I called it m last time and there were too many m's. Times, okay, m, NF, NF times little m. This was a mass. I'll call this little x. Turn on the superpotential, largely, and then turn on another then you flow down to some n minus 1 dimensional theory. Sorry, what am I saying? The theory with NF is equal to n minus 1. And then turn on smaller masses in that theory. Once you have the smaller masses, you have the vacuum expectation values of all the m fields, mij, where I runs from 1 to NF minus 1. Okay? You also know what the superpotential is. Because you know what the superpotential is, by equating that to x times m NF NF, you find m NF NF.
Here couldn't we have term like lambda by that m, the lower m?
We couldn't, because there was no Affleck-Seiberg superpotential for NF equals NC. All fields had Arshad 0. Right? So there was nothing other than this moduli space. Okay? So the superpotential you turn on is what remains. So you compare this guy with the superpotential you get underneath. You find m NF NF. You already used Affleck-Seiberg to find mij. So you've got the whole m. And now you just compute the determinant of m. And see is it 0 or not. Like we did last time, you find non-zero. But you find a universal number, which is 2NF, which is lambda to the power 2NF. This, I believe, is how he came about it. You know, the idea being, let's make it how can I make this physics consistent with what I already know to be true? Is this clear? Okay, and then the rest are checks. Okay, any other questions or comments? Of course it's not sufficient. You could get lucky. You could find 3 different theories that match the same anomalies so that you would know what to choose. It's not sufficient. But, especially when the numbers get a bit crazy, it's pretty convincing, right? I mean, it's a check. It's a check. It's certainly not sufficient. Certainly not sufficient. Okay. Do you remember Green-Schwarz anomaly matching from our class, Sunil? I don't know if you remember those numbers. Those numbers were so crazy that when we finally got 0, of course it's not sufficient to ensure consistency of that string compactification, but you feel, okay, if these numbers all cancel, we must be up to something good, right? I mean, that's the kind of thing that these numbers are less convincing. N square minus 1, okay. Maybe you can get them by consequence. Those guys had huge integers, right? Okay. No, but none of these are sufficient. You make a proposal and you check. But of course, these are all but your proposal has falsifiable predictions. And if they're not falsified, you feel a little confident that it's right.
But there is an argument that if you come from IR through RG, it doesn't change the anomaly.
Yes.
So can you ask the question that if you ask the reverse question,
yes,
that you, without changing the anomaly, how far you can go, like from the actual IR? Like, what is the set of IR theories?
I think there'll be an infinite set. Because we don't even know what the fields are, right? For instance, in QCD, at the beginning you've got quarks, then IR you've got pions. That depends on some physics. You could have some other physics imagination and produce some completely other fields. I don't think at all you should think of this as sufficient. This is one check of a proposal you make. But it's one check you can do, because anomalies are computable, so it's not to be scoffed at. Okay, fine. Okay, now let's move to NF is equal to NC plus 1. Please.
Here we check for 2 special points.
Yes.
Is there any proof or something like that?
There may be, as I was saying to Shoman, there may be that you can prove that, if it works in these points, it'll work basically anywhere else, because these look like the most symmetric points. Let's see, you can probably give an argument. You see, I think it would not be too difficult to just work the most general case out.
If there are less symmetries, then I think it will be in the subset of.
That's the style of the argument, I think. The only thing you have to convince yourself of is that tangent spaces have fields that transform similarly under the preserved symmetries. Because the UV part, the calculation is the same. Okay? You have to convince yourself that the IR part is also the same, which I think you could probably do if you thought hard enough. Right. Okay, great. Any other questions or comments? Okay, so now let us move to NF is equal to NC plus 1. This line was explicitly for NF equals NC, so we'll drop this out. Okay? Right. So now that we have NF is equal to NC plus 1, what do we have? What are the gauge invariant operators of the game? The gauge invariant operators, of course, are Mij, the meson matrix. And now we have also these baryons. But the baryons were, so let's say that we had gauge and flavor indices. Baryons always have always have come with NC quarks, so that they can be contracted with epsilon A1 up to ANC. So that is a gauge invariant. But because these fields were bosonic under complete interchange of all indices, they should be symmetric. So it's useful to do the following, to take epsilon I1 to INC, and then let's call this J, and multiply this with that. You're losing no information. Right? By antisymmetrizing, you're losing no information because it's automatically antisymmetric under interchange of flavor indices, because it was also antisymmetric under interchange of color indices. The whole thing was symmetric. And so you see that this guy here is a BJ. Okay? So how many different baryonic fields do we have? Unlike in the case NF is equal to NC, where we had one baryon field, here we have NC plus 1, which is NS baryon fields. Right? We have to make a choice of which quark not to put in, which flavor not to put into the contraction. Okay? So our gauge invariant fields are Mij, Bi, and B tilde j. Okay, these guys transform under the left SUNF, you know, the left flavor symmetry, and these guys transform under this and this transform under the left flavor symmetry, this and this transform under the right flavor symmetry. Okay. Now, first question we can ask ourselves is the following. Are these fields completely independent of each other? Okay, or are there constraints, which are the analogs of the constraint, the classical constraints that we had last time, which was det B is equal to det M is equal to BB tilde. Okay?
Here, B will be an anti-fundamental of SUNF because we have epsilon contracted.
B will be an anti-fundamental, correct, anti-fundamental of SUNF. Let's see, let me think that through. Yes, B will be in the anti-fundamental of SUNF, correct. These are, as you say, because of that comment, let's put the indices up. Mij, Bj. Perfect. Okay. So, the first question we can ask is, what is the, what is the relationship between these fields? Okay. Now, I'm going to claim a relationship, and then we will see where we got this from. B field, its gauge indices are all contracted. Now, the gauge indices that are contracted can't have equal flavor indices, because otherwise you would get 0. So all the flavor indices have to be different from each other. We have to one left over. It's the one flavor that does not appear in that contraction. Is this clear? Okay. Okay. Now, let's see. So, if you remember our solution of the D and F flatness conditions, Actually, just the D-flatness conditions. The solution of the D-flatness conditions up to gauge and global symmetry could be written like this, that if you looked at Q and you looked at Q tilde, you got A1 up to A. Now, let's suppose, I should draw, let's say this is color and this is flavor, suppose. I should draw it like this, right? There's one more flavor than color. Right. So one more flavor than color, so like this. So we had A1 to ANC. And this Q tilde also took the form A1 to ANC. Tilde. We could put the solutions of the D-flatness conditions up to gauge and global symmetry transformations in this form. Right? Now, this guy, in the previous cases, we had NF less than NC. So we had these A's ending like this, like they hit the bottom. A and A tilde were the same. I think you're right. Continue. Whatever was there, it's the same thing. Okay. A and A tilde was the same. Yeah, I think you're right. Okay, excellent. So now we've got this condition. We've got these configurations, and on these configurations, I'm going to see whether I can find some sort of connection. Okay, whether I can find some sort of connection between all these fields. Okay, so if I make this choice, this particular choice, there is only one baryonic field that is non-zero, right? It's the nth or nc plus 1th baryonic field, because we've got to get the product of all these other guys. Similarly with B tilde. Okay? And if I make this choice, this guy here, this baryon is the product of these various fields, these M fields. Right, so, sorry, this times this will become the product of the Mij. So M is diagonal with ijth entries. So let's see. So in this configuration, Mij would be equal to Ai squared delta Ij for I not equal to Nf, which is equal to Nc plus 1, and is equal to 0 if I or j is equal to Nc plus 1. Right? Also, we had Bi is equal to product I is equal to 1 to Nc Ai if delta I Nf, and similarly Bi tilde. Okay? Now notice the following. Notice that Mij on the standard configuration times B tilde j, this is a sensible contraction, because as Chintan pointed out, this transforms like fundamental and this transforms like anti-fundamental under SUNF. Okay, so it's a group symmetric transformation. Okay, this is equal to 0 because these Mij's are non-zero only when none of the indices is NF, but B is non-zero only when its index is NF. Right? Similarly, Bi times Mij is equal to 0 for the same reason. Finally, if we look at the minor, okay, the minor of the nth element, which I am formally going to write as M inverse times det M. Formal because neither det M exists nor does M inverse exist, but the minor exists. Okay, so this product in some sense exists, so at least the minor exists. Okay, then that is equal to what? The minor is equal to the product of all the remaining elements, the determinant of the remaining guys. And therefore it will be product of ai equal to 1 to nf square, which is same as b nf b tilde nf. Okay, and this we can try to write in a group covariant way. As SUNF times SUNF covariant way, as det M, which is SUNF times SUNF invariant, times M inverse Ij is equal to Bi B tilde j. Where always the meaning of the left hand side is as a minor. Is this clear? Okay, so classically the constraints on the moduli space, on the classical moduli space, the gauge if you parameterize it by the gauge invariant operators Bi and Bj, okay, if you parameterize it by the gauge invariant operators Bi and Bj, you will find, okay, classically you will find that these Bi's and Bj's are subject to the following constraint equations. So I'll just write that down, write down the final constraints again. And also okay. Now, the question we're going to ask, okay, the question we're going to ask is the following. What is the correct quantum description of this low energy theory? Okay, first I'm going to give you Seiberg's proposal, and then I will try to outline various arguments for in its favor. Okay, so first let me give you the proposal, And then we will try to understand why we think it's true. Okay. Okay. Proposal. These relations, which in the classical theory were somehow absolute relations, continue to survive unchanged but become floppy. What do I mean by that? Proposal is that the low energy theory is given in terms of Mij's that are unconstrained, these fields, Mij, Bi, Bj, all of which have no constraints. They're not constrained with each other. The field space is Mij, Bi, Bj, arbitrary. But there is a superpotential for these fields. Okay? And that superpotential is 1 over lambda to the right power. We'll talk about what that power is. Times, that superpotential is this, times det T, det M, minus the power of lambda is just, the power of lambda is there to set the dimensions correct, right? So just by dimension analysis we get that power of lambda. We come back to that power. There will be a way of thinking of it, but it's the obvious power. Right now let's focus on the non-trivial part of it. You might ask, where does this come from? Okay? To get some sense for where it comes from, let's compute the F-term equations from the superpotential. Let's compute the F-term equation from B. We get Mij B tilde j is equal to 0. Right? So F will be the derivative Fb will be the derivative of the superpotential with respect to B, and therefore will be Mij B tilde j, and in a supersymmetric vacuum we need F is equal to 0, so this must vanish on the vacuum. Is this clear? Similarly, the F-term equation, you remember what all you guys are now experts on the mechanics of supersymmetry, right? So the F-term equation is for B tilde tells us that Mij Bi is equal to 0. What about the F-term equation for M? Okay, tells us that det M inverse Ij, that's the variation with respect to M, the minor, minus Bi B tilde j is equal to 0. Notice these are the three classical equations. These are the three classical relations. Okay? So the first observation is that there exists a superpotential. Okay? That there exists a superpotential whose variation produces the classical relations. Right? So, Seiberg's interpretation of this fact, and we'll see many other ways of thinking. I mean, we'll solidify it in many ways. Seiberg's interpretation of this fact was that maybe the relations which were classically just absolute things, quantum mechanically emerge as dynamical equations of motion on a field space that had all possibilities, but emerge as the equations of motion on that field space rather than some absolute things. You know, this kind of thing happens often in dualities. In the simplest example of dualizing a U1, an uncharged U1 gauge theory, okay, the equations which were d mu f mu nu is equal to 0, which was an equation of motion, and the Bianchi identity, which in normal normal electromagnetism is hardly an equation, right? Statement of the obvious. These get interchanged under duality. So statements that were identities in one description turn into equations of motion in the other description. This often happens in the study of dualities. So this was the idea here. Okay? That the low energy effective theory sees classical physics, but not in the same rigid way that classical physics was, but as a sort of, in a floppy way, as in an equation of motion. Fluctuations don't respect that classical constraint. That's the idea. Okay, let's examine this proposal a little more.
But now is datum as an object is very different.
Mij as an object is supposed to be any field in the world. Okay? When you go to solutions of this equation, it will not be well defined. But that's just a property of solutions, of these solutions, not of the field. That's the idea.
Could one have written this superpotential by R symmetry?
That's what we're trying to do. That's what we'll now try to do. Excellent. So Diksha's question is that all through the earlier discussion of superpotentials, we obsessed with symmetries. Does this obey the various symmetries? So, okay. Firstly, it's obviously invariant under SUNF times SUNF times U1 baryon. Right, because it's built out of det M, which transforms in this det M way. We previously thought we couldn't have a det M because classically there weren't enough fields for det M. You remember, if you build M out of Qi alpha, Q tilde alpha, Q tilde J alpha, Mij is Qi alpha, Q tilde J alpha, then if the classical relationship is correct, then the M field has a rank no more than NC. And therefore, determinant of that M field vanishes. But the idea here is that this M now has left its classical moorings away, apart. Okay, it's a field, a genuine Nf cross Nf field, okay, which on shell may have the properties we're talking about, but off shell is free to fluctuate to arbitrary values. Is this clear? Okay, but its transformation properties are those that it would have inherited from the idea that it was this field, and so it transforms like fundamental times fundamental. Therefore, det M is invariant. Okay? Another way of saying it is that by prescription, M is a field that transforms like fundamental times fundamental, and therefore its determinant is invariant under. Okay? So under SUNF times SUNF, obviously invariant. Also the fact that these indices contract, the remaining indices contract, makes it obviously SUNF times SUNF invariant. Okay, U1 baryon is also obvious because M is invariant under U1 baryon and B and B tilde transform oppositely. Okay? So all that remains is to check the R charge. Now, let us remember what the R charges of various things are. Okay.
I was asking, could one have written a superpotential slightly more active than the superpotential? We have the lower degrees of freedom that we know, and now we're trying to construct something which has R charge.
Right. Okay, exactly. If we try to construct something, so let's write down the Affleck-Dine-Seiberg superpotential. Can you remind me what it was? What was it? Over that M to the power. Can you remind me what this power was? One over n. with a minus sign. No, correct. So let's take this Affleck-Dine-Seiberg superpotential, Diksha. This is minus 1. So this is that det M there. Okay? So if one were to construct an Affleck-Dine-Seiberg superpotential entirely out of M, it could only have been det M. In fact, this is the calculation I was going to do independently here to check that det M had the right R charge. But that's the same check that Affleck-Dine-Seiberg did. Okay? Notice, however, that in this case, we have additional operators. We have these B tilde operators. Okay? Now, if I want to make something SUNF times SUNF invariant, there are basically two choices. There's det M, and there's B tilde BI, MIJ, B tilde J. Right? Okay? So, there is another thing that we could have written, which was this B tilde MI. Let's check the charges of that. Okay. So, let's check the charges of this. Well, let's see. So, MIJ has the R charges of MIJ is twice that of psi. Psi was 1 minus NC by NF. So psi I had R charge 1 minus NC by NF. Now let's work in terms of NF plus 1 by NF. Okay, so psi has R charge minus 1 by NF. Okay, therefore MIJ has R charge minus 2 by NF. Right, because it's psi times psi tilde. All good? What?
Q times Q tilde.
Q times Q tilde, yes. I'm sorry, this was of Q and Q tilde, because I added the 1. Okay, what about the B's? B is a product of N, of NC, M's, NCQs. So B, the charge of B is minus N minus NF minus 1 by NF. Similarly, charge of B tilde. So if we add the charge of M with that of B with B tilde, we get minus 2 by NF, okay, minus NF minus 1 by NF minus NF minus 1 by NF, okay, and so we which is equal to minus 2. Now, did we want R charge 2 or minus 2 for the? Plus 2. What have I done wrong? Just one. Let me look. I clearly did it wrong because that was minus NC. NC is smaller than NF. Let me do it again. Minus NF minus 1. So plus what by NF? Plus 2 by NF. And then here, in fact, it wasn't cancelling, right? So this is plus, and now this and these cancel, right? Oh no. Even those will be plus. This was plus. No. Thank you. Let's see. So Q was this. Yeah. let me just do it this way. We agreed that the charge of Q was this. Now the charge of M times B tilde is how many Q's does it have totally? It has 2 plus NC plus NC. So it's 2 times NF. Okay, so 2 times NF. Yeah, so 2 times NF into 1 by NF. So it's adding up to 2.
You could have had similar term like we had before, which is like det M times some function of det M divided by this, and then we argued that.
Correct. Correct. So now your comment is that since we have 2 functions with the right R charge, now we have not determined the superpotential completely, because we could have arbitrary powers of arbitrary function of ratio. Okay, so this proposal here is consistent with R charge, but it is not fixed by it. Okay, so Chintan's point was that we could have written det M times function of B I M I J E tilde j divided by det M. We could have done that, no problem. Okay, and any function would have preserved R charge. The claim here is that this function is whatever it has to be to get det M by this, not completely fixed by symmetries. The answer we are proposing is allowed by symmetries, but it's not completely fixed by it. Okay, so we need further arguments to try to establish that that is the correct answer. One argument goes this way. When all fields are very large, all quarks are very large expectation values, gauge symmetry is completely broken down. Physics should be classical. In that case, the equations of motion that follow from this superpotential should be true classically. Right? Should just reflect something that is automatically true classically. Classically, there's no, if we look classically, there is no right. Classically, these statements, the statements that come from varying the superpotential, are just manifestly true in classical vacuum. That's some simple fact of algebra. So that statement should emerge out of this description if you have this sort of overarching kind of point of view. This is one other kind of consistency check of this, basic consistency check, that at very large fields, classical relations should emerge. And they do emerge because the equations of motion that follow from varying the superpotential are the classical identities. Okay? None of this is so far extremely convincing, although it's already quite nice, right? By the way, the power, you were asking about the power of lambda. Of course, it comes just from dimensional analysis, and it's also the power that you would get in Affleck-Dine-Seiberg. It's the same power. Okay. Now, let us move to try to get slightly more convincing evidence for this picture. Okay? The first thing we're going to do is the following. The first thing we're going to do is to take this thing. Okay, we won't have the time to do it this class. So let me just tell you what we're going to try to do, and next class we will complete it. In 2 or 3 classes we will complete our discussion of these Seiberg dualities. I hope it hasn't been too long and boring for you people. It's a very exhaustive discussion. I hope it's not been too slow. But, okay, so after that we will turn to discussing n equals 2 theories, Seiberg-Witten theory. Okay. Let me just tell you what we're going to do what we're going to do to get better evidence. First thing we will do is to take this description and try to connect to one lower flavor, as always. So what we'll do is to take a mass, take one of the quarks and give it a mass. Once we add the superpotential that gives that quark the mass, we will now resolve for the vacuum expectation values of all these m's and b's. And we will show that that resolved solution, okay, will automatically lie on the manifold det m minus b b tilde is equal to 2 lambda, is equal to lambda to it. Okay, thereby automatically demonstrating that if we added more masses, it will automatically agree with everything we know at lower energy. This is really the most convincing check. The check is that we've got a description which if you, well, a very convincing check. We've got a description such that if you give one of the quarks a mass, it goes back to, the description agrees with what we know. Okay, this is first thing we're going to do. Second thing we're going to do is to do anomaly matching. Okay, now the anomaly matching check is a very different one from what we had previously. See, the anomaly matching for NF is equal to NC was a bit trivial because the manifold of, you see, the manifold of vacua was basically what you got from a small deformation of the classical relations. So it's not very surprising then that fluctuations of psi tilde reproduce fluctuations of this m. Because the m is exactly what it would have been had it been made out of psi and psi tilde. Right? But in this case, the anomaly matching condition is going to be more interesting. Because there are more fields available to fluctuate on. You'll see how this works.
So you are saying just from m equals to q tilde we had determinant to be 0, but here it's
here,
far from.
Yeah, right. Here, well, I said something a bit inaccurate, something I need to. Let's just say how it works next class. We're going to do we're going to do lots of anomaly matching checks. Okay. One thing to say, one thing that makes it more non-trivial is this. This set of relations allows for the point m is equal to 0, b is equal to 0, b tilde is equal to 0. Right? Because the classical relations are just undeformed. Notice by the way, that was the case. In the case NF is equal to NC, the classical relations were deformed. Here, the relations that come out of varying the superpotential, which we're claiming is exact, give us back the classical relations, which means that they are undeformed. We reinterpreted them, but they are undeformed. Okay? So, here, we will be able to perform many more anomaly matching checks. Because there will be a point in the moduli space of vacua where all symmetries are preserved. Okay? And you will see when we work out the anomaly matching check next class, this somehow feels a bit non-trivial to me. And that's going to work in a very impressive way. I'll explain more why I think it's non-trivial next class. It's a question of what the manifold is. You will see. Okay. Okay. So these two things, A, is that adding a mass to the theory gives us back what we knew to be true at NF less than N's, a smaller NF, and anomaly matching will sort of convince us that this proposal is true, more or less. Okay? The other thing, of course, about all these things is they form a tight web. So when we look at, then in a subsequent class, we will look at NF greater than, NC greater than NF plus 2. And we will discuss even more interesting phenomena, an even more interesting proposal, that of electromagnetic duality, two different descriptions of the same IR physics. And we will also see that that proposal matches NF is equal to NC plus 2 proposal. Anyway, yeah. Okay. Okay, thank you.